Hi, welcome to Chapter 14, Chemical Kinetics, Overview Part 2, where we're going to talk about concentration and rate laws. So, how do you determine the concentration effect on rate? So, in order to determine the effect of concentration on rate for each reactant, you have to do a bunch of experiments. And in those experiments, you have to vary, say you're varying the concentration of NH4 plus, you have to keep the concentration of NO2 minus constant. So we keep every concentration constant except for the one reactant that you want to see what happens to. Then we change to a different reactant and repeat that process all over again. So one can gain information about the rate of reaction by seeing how the rate changes with changes in concentration. So here's some data where we have performed 8 experiments varying the concentrations. To determine how the concentration of a reactant affects the rate, we compare the same reactions with different reaction concentrations. So, for example, you would compare reaction 2 to 1, and you see here we're keeping this term constant, so we could figure out how NH4 plus changing the rate or doubling it affects the overall rate. So, as we double the concentration of ammonium, what happens to the rate? So here we're doubling the concentration. We went from 0.01 to 0.02. Let's look at the rate. We went from 5.4 to 10.8. So this was doubled. And if you multiply 5.4 times 2, it was also doubled. So as ammonium was doubled, the rate doubles. Now let's do the same thing, keeping ammonia constant, and look at NO2 minus. So that's what the circles in the blue. See, these are constant. So, and we doubled the amount of NO2 minus. What happened to our rate? Well, if you do 10.8 times 2, you're going to get 21.6. So as this concentration doubles, the rate doubles. This means that the rate is proportional to the concentration of both NH4 plus and NO2 minus. So by looking at experiments 1 to 3, we could figure out, looking at the concentrations of our two terms, NO2 minus and NH4 plus, we figured out that as NH4 doubles, the rate doubles. And we did that by taking a ratio. The rate 2 divided by the rate 1 is equal to the concentration in experiment 2 divided by the concentration in experiment 1. And when you do that, we're trying to figure out if this is raised to some exponent x. So when you divide these two rates, you get 2 is equal to 2 raised to the x. So the only value of x that'll give you 2 is if x equals 1. Then we do the same thing for NO2. Okay, so in this case, we're going to compare, let's see, we want to keep, so 5 to 4, we'll compare those two. So we're going to take the rate of 5 and compare it to the rate of 4. And you see this is constant, so we could ignore the concentration of it. So we're going to have the concentration of 5 raised to the power, that's what we're trying to look for, is equal to the concentration of 4 raised to x, and that's going to equal so sometimes you could just do it in your head. So you see here, this is 2 raised to the x equals 2. So in this case, our exponent is also 1. So what is our rate law? So the rate is proportional to the concentration of ammonium, and it's proportional to the rate of the concentration of NO2 minus. So the rate is actually proportional to both of them times each other raised to the exponent 1. So here is our official rate law for that reaction. This equation is called the rate law. K is the rate constant. Remember, this depends on temperature. So a rate law will show the relationship between the reaction rates and the concentration of the reactants. The exponents tell you the order of the reaction with respect to each reactant. If the exponent is 1, it is first order in that substance. So for both of these reactants, it's first order in each of them. So the exponents tell you the reaction order. In our example from the last slide, we had our rate is equal to K times concentration NH4 raised to the 1 and the concentration of NO2 minus raised to the 1. So with respect to each reactant, it is first order. Overall, the overall reaction, you add your orders together. So the overall, it is second order because each is raised to the 1, so you do 1 plus 1 and get 2. That is called your overall reaction order. So overall, this reaction is second order. Although the coefficients in the reactions are sometimes the same as the rate law exponents, that is not always the case. Whenever we're trying to solve for these exponents here, you don't look at your balanced equation. You must use experimental data. Must. So remember, the order is not equal to stoichiometry. Look at this example here. Here we have a 2, a 4, and a 1 here. So the rate that this reaction is going at is not the concentration of N2O5 raised to the 2. It is not. So you can't just look at these coefficients and make them the exponents. You have to use experimental data. Okay, look at this one. The exponent is 1/2. This is not, there's no 1/2 here at all. What is K? K is the rate constant and it is temperature dependent. So when they're giving you concentration data, they normally state it at a certain temperature. The rate constant is often used to determine the relative rates of a reaction. What is the value of the rate constant K? Well, if your value of K is 10 to the 9th or higher, that is really telling you that your reaction is fast. If it's lower than 10, then that is telling you your reaction is slow. Okay? And the units of K change. These units change because it depends on your rate law. So, for example, the rate law we just did, each of these are first order. I know my rate has to have units of molarity per second, right? And I know each of these concentrations are molarity. So I need molarities per second. I have K. I don't know what its units are, but it's times molarity squared because each of these are molarity. So K has to kind of fix the units so I get molarity over second. So in this case, the units of K are 1 over molarity times second. So your unit K really depends on your order. So if you change your orders here, then your molarity here on the bottom is going to be either squared or different. So in general, the units for your rate constant is equal to the units of your rate divided by the units of your concentration raised to the total reaction order. So let's look at an example. If I have this following rate law, the rate is K times calcium squared, or to the second order, times the concentration of sulfur. If I double the concentration of sulfur, what happens to my rate? Well, if I double this isn't S anymore, this is 2S raised to the 1. So my rate will double. If I double calcium, so this is no longer calcium, this is 2 calcium, but you have to square all that. So 2 squared is 4. So my rate will be 4 times faster. So the order is important. So let's do a sample problem together. So here is 4 experiments where you're varying the concentrations. We have 3 reactants here. So my generic rate law is going to be K times the concentration of BrO3 minus raised to some exponent x times Br minus raised to y times H plus raised to z. okay? I can't use the coefficients. I have to use my data. So you want to pick some reactions where only one of the reactants concentration is changing and the other two are being kept constant. So I'm currently looking at reaction 2 and 1. These two are constant and these two are constant. So only BrO3 is changing. So what I'm going to do is compare, and you always want to put the one that has a larger value on top. It just makes doing the math easier. So I'm going to compare reaction 2 to reaction 1. So remember my rate law is, and for this example, I'm going to write it all out. Actually, instead of writing this, I'm actually going to write the concentrations in there. So the concentration is 0.1. Actually, it's 0.2. We're going to do 2 first. Do this one here. Times 0.1 raised to the y times 0.1 raised to the z. And let's compare it to reaction 1, which is 0.1 raised to the x, 0.1 raised to the y, 0.1 raised to the z. And that is equal to rate 2 divided by rate 1. So you see here, these cancel out. So for the next one, I'm not going to write the ones that cancel out, but I wanted you to be aware. These cancel out and k cancels out. So what am I left with? 0.2 divided by 0.1, all raised to some power x, is equal to, well, when I divide this, I get 2. When I divide this, I get 2. So 2 to the x is equal to 2. So in this case, x is 1. So I'm going to come over here, and x is 1. So I'm just going to erase the x. If it's a 1, you don't have to write it. Now I have to repeat this process to try to find the constant, to try to find y. So we want Br to vary, but we want everything else to stay constant. So in order to do that, let's see. How did I do that? 3. Nope, 3 to 1 would be this one. Yep, 3 to 2. So for this one, I'm going to do it in a different color. So we're going to compare 3 to 2. See, these are staying constant, and these are staying constant. So I only have to worry about Br. So now I'm going to, again, put the higher one on top because it makes math easier. So I'm going to compare rate 3 to rate 1. So I have 0.2 raised to the y divided by 0.1 raised to the y is equal to 3.2 times 10 to the minus 3 divided by 1.6 times 10 to the minus 3. So this gives me 0.2 raised to, 2, oops. No point, just 2 raised to the y is equal to 2. So y is 1. So that means I could erase this y here and put a 1 there, but 1 is understood, so we just leave it as such. Okay, now I have to figure out the exponent for H plus. So let's do that in a different color. Let's do green. So we have to find 2 reactions where everything's constant except H plus. So we're going to use 4 and 1. So let's compare the rate of 4 to the rate of 1. So here we have 0.2 divided by 0.1 all raised to z is equal to so we have 2 raised to the z is equal to 4. So here z is 2. So we come over here, and we raise the z, and we make it a 2. So here is our rate equation. Determine the overall order of the reaction. So the total overall is adding them up. 1 plus 1 is 2 plus 2 is 4. So 4. Okay. Now determine the value of K, the rate constant K. So we have our rate law. And we have the rate and the concentration. So just pick one. So I'm just going to pick the first one and plug in the data for it. So my rate is equal to K times the concentration of the first one times the concentration of the second one times the concentration of the third one squared. Then you rearrange everything and you get that K is equal to 8 and the unit is 1 over molarities cubed seconds. Okay, now they're giving me concentrations and want me to actually calculate the rate. So now I know my K is 8 and the rate of BrO3 is 0.2, the rate of Br is 0.48, and the rate of H plus is 0.32 squared. So when you plug all that in, you're going to get a rate of 0.079 moles per second. And that is the end of part 1.